Hi, everybody. So I'm Timothy Jordan. I'm a developer advocate, and I'm not an expert in machine learning. And I think that's what's so cool about this presentation and where we're at with machine learning today. Is as long as you know how to use an API, you can get started with machine learning with your app today. And if you want to go deeper and develop your own models using your own data, TensorFlow can help you do that. I'm going to start with an overview of machine learning at Google that you can use. And the landscape, it looks like this. First, there's mobile vision. It's ready to go, and it runs locally on the phone without needing to communicate to an external service. You can detect faces, scan barcodes, recognize text, all within your mobile app. Here's an example of adding cartoon eyes to an image. And to do this, it's as easy as calling an API to get the pixel coordinates of the person's eyes. Now, this is powered by machine learning under the hood, but you can take advantage of it without needing to know the details. There's also the Google Cloud Platform. And there's two parts that you want to know about. First, there's ready-to-use machine learning models for speech, vision, and translation. Also, there's cloud machine learning, currently in alpha. Now, it's particularly great for training your own models quickly and serving at scale. Now, these APIs are all really powerful. Label detection, for example, is really cool. You just upload a picture, and the API will tell you that there's a cheetah in the image. Now, like mobile vision, you can use these APIs without knowing machine learning, how it works. You just need to know how to access the API. And of course, there's TensorFlow. TensorFlow is the open source machine learning framework released by Google late last year. And it's already the most popular machine learning library on GitHub. It has a vibrant community. And with TensorFlow, you can use existing models, train your own, develop new ones, serve them, or even learn machine learning for the first time. Now, one thing that's special about TensorFlow is that it's used by both researchers to develop new algorithms and by developers to build machine learning-powered applications and services. Now, we'll cover these things in this talk. I'm going to go through a few examples of machine learning that I think are cool, just to give us an idea of the spectrum. And then we're going to write Hello World with TensorFlow. And we're going to do it quickly. But as I think you'll find, it's really easy to do. All right, let's start with some examples of machine learning. As you see with mobile vision and cloud vision, image recognition is a big deal in machine learning right now. But what if you wanted to train a model to recognize images with your own data set? Well, you can use that using TensorFlow. In fact, Google open sourced one of the best image recognition models in the world, and it's called Inception. And we've included a pre-trained model so you can start playing with it right away, as well as the architecture and code to train it on your own data. Now, you might have heard of Deep Blue, the first computer to play chess at a championship level, but Deep Blue defeated their opponent mostly through brute force, by having a tree of moves that they could make. Now, I think everybody here knows about AlphaGo. Yes? No? It was here. It was down the street. Now, Go, as you know, is much more difficult than chess to try and solve by brute force model. In fact, I think you could safely say it's pretty much impossible. So we use machine learning. And the machine learning algorithm for AlphaGo actually examines the board visually, somewhat like a human would. And it uses vision to see what makes a good board position, and then uses that insight to search the game tree more efficiently. Now, in addition to recognizing images, machine learning can also be used to generate them. Like, what if you tried to generate the image of the United Nations on the left, but in the style of Picasso? It might look like this. And by the way, you can do this with TensorFlow today. This is what happens when you kind of It's sort of like running the algorithm backwards, so that instead of the machine learning algorithm telling you what it sees, it writes what it sees into the image. Another cool example of this running it backwards, you may have heard of Deep Dream. And this is what you get when you run it backwards and you see all the things that the algorithm can recognize start to show up in the image. And of course, back to some practical applications, machine learning can be used to understand language. Now, this is the world's most accurate syntax parser in action. It's called Parsey McParseface, which is a really funny name in English. I hope it translates. And it can analyze sentences, telling you things like what the direct object of the sentence is. Even more everyday, these are some Google applications that you may have used, such as recommending artists and play music, recognizing spam in Gmail, recognizing the contents of your photos and making them searchable, speech recognition, text recognition and translation, even guessing and suggesting what your responses will be on email. In fact, all these technologies are powered by an approach to machine learning called deep learning, which we'll talk a little bit later. Now, we have over 60 projects that have been using deep learning technology at Google. It's not just academic research anymore. It's reliable and scalable production technology. Okay, let's write hello world with TensorFlow. Does that sound like fun? Okay. We'll write code to recognize handwritten digits, like a 1, a 2, or a 3. Now, this is a classic problem in machine learning, and there's a great data set available to play with it. Now, as humans, we take vision for granted, but it's actually pretty hard, right? To us, a picture of a 1 looks like that on the left. It looks like a 1. But to a computer, it's going to be a collection of pixels. Right? This is a large matrix, well, actually a pretty small matrix. It's 28 by 28, so 784 pixels. And each pixel is grayscale, so it's a floating point number between 0 and 1. Now, for that reason, because it's that matrix of pixels, it's really difficult to solve this code with control flow structures. Right? It'd be difficult to write manual rules. For example, you wouldn't want to write lots of if-else statements for every pixel. It'd be crazy, right? And in fact, arguably impossible to do it at any level of accuracy that would be interesting. There's lots of different handwriting styles. Images can be taken from different orientations. There's lots of things that make this even more complicated than just the pixels. So we're going to use machine learning. This is one of the reasons it's a classic example of machine learning. We're going to start with some data. In fact, we're going to start with 60,000 images of a digit, each with a label of what digit they contain. So there's an image, and then the label is 0 through 9. And we're going to split this up into two groups, some for training on the left, and some for testing on the right. We're then going to select a statistical model, or what we call a classifier. And in this example, we're going to use what's called a linear model. Now, there's many types to choose from, but this is a good example since it's relatively simple to implement and understand. We'll then use the training data to adjust the parameters of the model or to learn them until it's able to classify most of the examples correctly. Now, this is the heart of machine learning right here, and I'm going to talk about this in more detail. We'll then test the model on our test data. And then we can use it to classify new data. And that's machine learning. So here's the complete code to do all of that. It's just 6 lines of TensorFlow. Now with this, we get about 90% accuracy, which is pretty good. I mean, it sounds kind of great, but you can get way better in TensorFlow. In fact, with some algorithms in TensorFlow on this same data set, we can get over 99% accuracy. But I wanted a quick example, and I think this is a great way to get started. Now, there's a bunch of different ways to write TensorFlow code. You should know that this is what we call TensorFlow Learn. It's a high-level ML library on top of TensorFlow, so it makes it a lot simpler and easier to get started. Now let's look at what each of these lines do in turn. First, we're going to import the MNIST dataset. Now, as I mentioned earlier, this contains 60,000 28 by 28 images in two parts. The train, which we'll use to learn the parameters of our model, which contains 50,000 of the images. And the other part is test. It contains the other 10,000 images, and we'll use these to see how accurate our model is. Now, in this line, we're going to initialize the linear classifier, and this is how it works. First, we'll flatten the image. And the MNIST data it's really a 2D array, right? But we're going to flatten it into a 1D array of 784 pixels. It just makes it easier for the linear classifier. Now, we do lose some information doing this, and there are classifiers that can handle two-dimensional data, and they would do a better job. It would be higher accuracy. But again, we're going to simplify it here, and we'll still get pretty good accuracy. Now, each pixel becomes an input node, which you see on the top of the diagram there. Now, remember, the pixel values range between 0 and 1. Now, the output nodes are on the bottom. We have 10 of them, one for each type of digit, 0 through 9. Now, here's where it gets interesting. Each input node is connected to each output node by a line or edge. Here, I've just drawn from the first pixel to all the outputs. Now, each of these has a weight. The weight roughly indicates how likely this image is to be each digit, depending on the value of that pixel. Now, for example, if we're talking about an 8 right there in the left, notice that because there's 4 lines crossing in the middle, it's pretty likely that you'll have filled in pixels at a high value in the center of the image. Now, we'd expect those pixels, when connected to the outputs, to have higher weights. Makes sense, right? Now, this is fully connected. This is where we've drawn all the edges to all the outputs. And the weights are no longer shown, but each one will have one. And initially, we start with random weights. To predict the label for each image, we multiply each input value by its weight and sum up the evidence for each output node. Right, so just to make this super clear, the input, this is the input, that's the value of the pixel. And then this is the weight, that's the value of this edge. Multiply those, sum up all the inputs into the output, and of course, the highest number is likely the output. But we're starting with random weights, so when we start, it's horrible accuracy. There's no prediction whatsoever. So what we need to do is find the right weights for all of these lines that makes this model work. Now, that's called training the model, and that's where machine learning really happens. That's the heart of it. Now, the fit method is what takes care of that for us. Here's an idea of how it works. So this is a plot of the number of errors that our classifier makes as a function of the weights or the parameters. Here we've just shown 2 weights, right there, right there. And let's say we start with the random values as we do. If we adjust them slightly, we can see if our error over here on the left goes up or down. If it goes down, we keep moving in that direction to reduce the error of our overall model. Now, we can use calculus to determine which direction to adjust the weight so that we can do this efficiently. The algorithm is called back propagation, and it can be used to train a linear classifier like ours as well as a deep neural network. Now, I think this is really key, so here's another way to think about it. Imagine if we were to embody this algorithm. We're standing on a mountain, and we want to get down the mountain, but there's fog all around us. All we know then is if we walk one direction, if it goes down or not. So we walk the direction that goes down the most steeply. That's going to have the least errors. And by using this method, we can quickly reduce the overall error of our graph and get closer and closer to a model that gives us higher and higher accuracy. Does that make sense? I see some nods. I like those nods. Okay. Now, once we've learned the weights, we'll use our trained model to classify every image in the testing set. And then we'll compare the predicted label with the actual one, and that's how we get our accuracy. Now, here we get 92%. Again, this is fine for 6 lines of code. But with a few more, we can get over 99%. For example, with TF-Learn, we can actually switch to a deep neural network, right? That's deep learning with a single line of code. That's this one right here. You may ask, what's a deep neural network? Well, neural networks sound fancy, but they're just a statistical model, just like our regular network. Regular machine learning with our classifier connects the inputs, or the pixels at the top, to the outputs directly. Deep learning is simply adding more hidden layers in between. Each of these is a neuron that perform operations on the weights of the edges between them. Now, to build the model, we just do a similar operation as before to learn all the weights between all the layers. And that's deep learning. Pretty simple now that we have the foundation, right? Now, to learn more about deep learning, we actually have a great Udacity course called, and you just search for deep learning on Udacity. And you'll find it, and it'll go into way more detail than just my overview here. In fact, there's a lot of great tutorials at TensorFlow.org. If you want to go from where you're at today, check out MNIST for beginners. And it'll show you how to write lower-level TensorFlow code for the same problem that we looked at today. You can also check out MNIST for experts, and you can see how to get over 99% accuracy, again, with the same data set. Also try the TF-Learn Quick Start, which is very similar to what we looked at today. And you can even experiment with deep neural networks in your browser using the TensorFlow Playground. This thing is really cool. It's a neural network that you can run in your browser, and you can use it to classify points on a 2D graph. And it's great for experimenting, adjusting the parameters of the network, like how many layers it has or how many neurons, to really learn how the deep neural network's parameters adjusts your output. And the computations that you use in TensorFlow, like training a massive deep neural network, can be complex. To make it easier to understand, debug, and optimize TensorFlow programs, we've included a suite of visualization tools called TensorBoard. You can use TensorBoard to visualize your TensorFlow graph, plot quantitative metrics about the execution of your graph, and show additional data like images that pass through it. Let's say you've trained an image classifier like Inception or like on the MNIST data, and it's running on a server with lots of incoming requests from clients to classify images. TF Serving will help you handle those efficiently. It also supports a lot of advanced functionality as well. And mobile TensorFlow is available so that you can run the models that you build in TensorFlow on the mobile phone as well. And this lets you go beyond the stock applications of something like Mobile Vision to your own custom data. And here's some additional URLs, guides and code labs, and TensorFlow. I hope that was a great overview and that you understand machine learning and deep learning better, and I look forward to seeing what you create with it. Thank you so much.